Welcome to the Deep Dive. We're here to break down some big ideas in science, getting right to the core concepts. Today, we're jumping into a really foundational chapter from the Feynman Lectures on Physics, Volume 1. It's Chapter 11, all about vectors. Now, our goal isn't just, defining a vector. You might already have a sense of that. We want to get at the why. Why are vectors so essential in physics? And the answer, maybe surprisingly, goes deep into how physics views the universe through symmetry.
That's exactly it. It's a really pivotal moment. We're looking at moving from describing laws with separate x, y, z components, which can feel arbitrary, to this unified vector notation. A notation that inherently respects the symmetries of nature, meaning the laws look the same no matter your viewpoint. The focus here is the logic, not just memorizing the equations.
Okay, let's dive in then, starting with that foundation you mentioned. Symmetry. What does Feynman mean by symmetry here?
Well, in physics, symmetry means you can do something like shift your experiment over or rotate your whole setup, and the underlying physical laws don't change. They stay exactly the same.
Like the left-right symmetry of a vase Feynman mentions, you flip it, it looks the same?
Precisely. And he starts proving this invariance mathematically with the simplest case, translational symmetry, section 11 to 2. Basically, it asks, do the laws of physics care where you are in space?
Right. The thought experiment with the two coordinate systems, Joe and Mo. Mo's system is just shifted over from Joe's by a fixed amount.
Exactly. So Joe writes Newton's second law, maybe just for the x direction. Dollar times the second derivative of 6 equals the force in the x direction, fixed dollars last. Mo does the same, but with his coordinates, $6. Now, the connection is simple. $6 is just $6 minus some constant distance. Let's call it $6.
X is X. Okay.
And here's the key mathematical step. Because Mo's frame is just shifted, not accelerating relative to Joe's, that $6 is constant. So when you take the second derivative with respect to time to find acceleration,
Yeah, the derivative of a constant is 0. That stellar one's term just vanishes.
it just drops out. Exactly. So Joe's measured acceleration, 2 plus dt2, is identical to Mo's, q plus dt2. And the implication is huge. It proves the laws of physics don't depend on a fixed origin. There's no special center of the universe, physics-wise. Like being on a smoothly moving train, the physics inside works just the same.
Okay, translation feels, well, almost obvious once you see the math. But rotation, that seems trickier. Let's talk rotational symmetry, section 11 and 3. Now, Joe and Mo's coordinate systems are rotated relative to each other, say, by an angle theta.
Right, and this brings up that immediate objection. If I tilt my bathroom scale, the reading changes. It seems like rotation does matter. But Feynman points out, that's not the fundamental law failing. That's your scale interacting with something external, like Earth's gravity, or maybe even the Earth's rotation itself. Your measurement isn't isolated.
Got it. So the fundamental laws in isolation must be symmetrical under rotation, even if our everyday experiments aren't perfectly isolated.
That's the principle. And when you work through the math, which involves relating Joe's force components, fixed x for cheese, the Mo's 5 capi fec y, FCOAC, using trigonometry for the rotation, you find the same result. Newton's laws hold true. The form of the law is invariant under rotation. It doesn't change.
Okay, so we've done all this work with shifting and rotating coordinate systems.
Yeah.
Joe and Mo have been busy, and we've found that the laws themselves don't care about these shifts or rotations. So why did we need all that coordinate math?
Because it reveals the need for a better way. We need a mathematical language to describe physical things like force or velocity that automatically reflects this indifference to coordinate systems. We need objects whose descriptions handle rotation correctly without us having to recalculate components every time.
And that is where vectors come in. Section 11 to 4. This is the payoff for understanding symmetry.
Exactly. Now we can define quantities based on how they behave when you rotate the coordinates. First up, scalars. These are the simple ones, just a single number, magnitude only. Think mass, temperature, energy. Rotate your axis all you want, the temperature is still the same number.
Unchanged. Easy enough.
Then we have vectors. These are quantities that need both a magnitude and a direction. Things like displacement, velocity, force, momentum, typically represented by 3 numbers in a given coordinate system, the components, 6 doxers, y, z, del.
Okay, wait. Magnitude and direction. What about something like electric current? It has a magnitude and flows in a direction. Is that a vector?
Fantastic question. It highlights a crucial subtlety Feynman emphasizes. Having magnitude and direction is necessary, but it's not enough. The absolute defining characteristic of a vector is its transformation property.
Meaning?
Meaning when you rotate the coordinate axis, the components of a true vector quantity must transform using the exact same trigonometric rules that we use to transform the coordinates, 6 doctors YZ themselves, between Joe and Mo's rotated systems.
I see. So electric current, while it has direction, its components don't follow those specific geometric rotation rules, so it's not a vector.
Precisely. That transformation rule is the non-negotiable part. It ensures that the vector quantity represented by a bold symbol like F or V stands for the same physical arrow in space, independent of how you happen to draw your axis. It's observer-independent reality.
Okay, that clarifies the definition. So now that we have these axis-proof objects, how do we work with them? Vector algebra, section 11 to 5.
The algebra rules are designed to preserve this vector property. For adding vectors, a plus b, you can visualize it with the head-to-tail method or the parallelogram rule. The key thing is that it's commutative. A plus b is the same as b plus a, which makes physical sense. Walk north then east gets you to the same place as walking east then north.
Right, the math matches reality. And subtraction, AB, is just adding the negative vector, A plus B, where method 3 points the opposite way.
Simple enough. Now let's apply this to motion kinematics. If position is a vector r, an arrow from the origin to the object, then velocity is its time derivative.
V equals dr dt, a vector quantity.
And acceleration is the derivative of velocity, a equals dv dt, also a vector. And this leads us to the real elegance of vector notation in section 11 to 6. Remember Newton's second law? We used to write 3 equations. Fifth Lx 5 equals ma, fevlix equals raz.
Yeah, one for each dimension. A bit cumbersome.
But now, because we've proven force F and acceleration to transform correctly as vectors, we can write one single powerful equation, F ma.
Wow. So that bold font isn't just for show. It packs in all that coordinate transformation invariance automatically?
That's exactly it. It's a statement that's inherently true in any coordinate system Joe or Mo might choose. It frees us from the bookkeeping of components and lets us focus on the physics.
That is pretty neat. Okay, so how does this vector view help understand something like moving in a curve, section 11 to 6 again?
Right. If an object's path is curved, its velocity vector v is changing, even if its speed. The magnitude of v is constant.
Because the direction is changing.
Precisely. So acceleration, which is the change in velocity over time, delta math bf delta t phi, must exist. And vectors help us dissect this change. Think about that velocity change, delta math bf. It can point in 2 fundamental directions relative to the motion.
Okay.
First, there can be a component of acceleration parallel to the velocity vector. This is the tangential acceleration. It happens if the speed is changing, hitting the gas or brakes.
Right, changing the length of the velocity arrow.
Second, there can be a component of acceleration perpendicular to the velocity vector. This is the radial acceleration. It happens purely because the direction of velocity is changing, like turning the steering wheel.
Ah, even if you keep the speedometer steady, the change in direction itself is acceleration.
Exactly. Vectors force you to recognize these 2 distinct ways acceleration happens. And for the special case of moving in a circle at constant speed, all the acceleration is purely radial, pointed towards the center.
And Feynman gives the magnitude for that case, a v2r2, where r is the radius. A clasp result derived naturally from the vector picture.
So we can add, subtract, differentiate vectors. What about multiplying them? Section 11 to 7 introduces the first way, the scalar product or the dot product.
Scalar product, meaning the result is a scalar, a single number.
That's right. You take 2 vectors, multiply them this specific way, and you get a scalar quantity, a number that doesn't change when you rotate the axis.
Okay, how's it defined?
2 equivalent ways, which is crucial. First, the component form. You multiply the corresponding components and sum them up. Math BFA, C dot, Math BFA fiat, Math BSB, TFA stiat, JWA DAO, plus ASB DCat. You feed in 2 sets of 3 components, which depend on your axis, but the final sum is miraculously independent of the axis. It's a true scalar.
Okay, components matched up and added. What's the other way?
The geometric form, which is often more intuitive. Math BGBFE Ciat, Math DSD. Here, A2 and DFD are the magnitudes and length of the vectors, and the lambda is the angle between them.
So it measures how much the 2 vectors line up. If they're parallel, you get the maximum product to add B. If they're perpendicular, the dot product is 0.
Exactly. It captures the projection of one vector onto another. And using unit vectors, Math BFG, it makes this clear. Math BFG, Math BFI, but Math BFD, Math BFJ.
So why is the scalar product useful in physics? Where does it show up?
It's fundamental for defining scalar energy quantities from vector motions. Think about kinetic energy.
KE, 12 meters a square.
Right, but using vectors, it's properly $12 meters, the dot product of velocity with itself. Since Math BFE as she gives e to 2, magnitude squared, which is a scalar invariant, Kinetic energy is correctly defined as a scalar, observer-independent quantity.
Makes sense. Any other big ones?
Work. The physical concept of work done by a force F moving an object through a displacement S. Work is defined as the dot product.
Yeah.
Door math BFF VFGEC. This automatically captures the fact that only the component of the force along the direction of displacement does work. If you push perpendicular to the motion, no work is done by that part of the force.
It elegantly handles the alignment aspect. Okay, this really ties things together. So quick recap. We started from the idea that physics looks the same if you shift or rotate your viewpoint symmetry. That symmetry demanded a mathematical tool, the vector, whose components transform in a very specific way under rotation, matching how coordinates themselves transform.
Exactly. Scalars just need magnitude. Vectors need magnitude and this correct transformation rule for their direction, represented by components. This allowed us to write laws like math BFSA universally, without getting bogged down in specific coordinate choices. We used vector algebra and calculus, and then the dot product to link back to scalar quantities like energy and work.
We covered the scalar product, math BF beat dot, which results in a scalar. But Feynman mentions another type of vector multiplication, the vector product or cross product, is coming later.
Yes, that's deferred. So here's something to think about. If the dot product yields invariant scalars related to energy and alignment, what kind of physical principle needs a multiplication that produces another vector? What invariant physical quantity requires not just magnitude, but also a direction that must itself transform correctly under rotation? That's the puzzle the vector product will eventually solve.
A great question to ponder. What physics needs multiplication that results in a direction? Thanks for joining us for this deep dive into the necessity of vectors.